Welcome to this video. The thermal machine that this video is about essentially consists of 4 cylinders with their pistons, because there are 4 phases that each cylinder carries out: suction, compression, expansion, exhaust. A chemically inert, high-yield working gas is used to produce mechanical work, and the horizontal arrows at the top of the cylinders indicate the respective solenoid valves for the inlet and outlet of the gas. The crankshaft at the start is in a configuration designed to carry out the phases in all cylinders. Obviously, it is also possible to make different configurations if imposed by mechanical requirements. The discs on the left side in red are optical, or possibly other, and are used to generate input signals for the CPU that will manage the on-off of the above solenoid valves. The green disc on the right is a flywheel to which a traditional boot system is connected. The system in the initial configuration required for startup. The 5th cylinder in blue contains the working gas which is sent to the cylinder in orange via the valve in blue. In fact, at the initial moment the cylinder in orange simulates gas compression. At startup, the starter motor will simulate expansion work in it and compress the gas in the cylinder in green for future true expansion and thus for starting the entire system. The cylinder piston in blue will remain stationary at the end of its stroke throughout the operation of the machine, and the valve in blue will remain closed after the gas has passed. The vertical arrows on the cylinder heads represent the external heat sources. Between the mauve cylinders there is a connection for gas exchange in red. An internal heat exchanger, in white, is represented for the recovery of part of the waste heat. This is done after the gas has passed through the external heat exchanger, in brown, to return to its initial state. It can easily be demonstrated that the gas exchange zone between the 2 cylinders constitutes a unique and physically isolated environment from the point of view of the forces and moments applied to introduce further quantities of working gas in a calibrated manner. From now on, the process is repeated cyclically ad infinitum by successive stages. The main advantages of the machine are: 1. Zero emissions. 2. High efficiency. Efficiency levels close to the theoretical Carnot cycle can be achieved. 3. Lack of destructive internal stress due to the absence of bursts. 4. Quiet operation. 5. Use of advanced mechanics and possible use of non-metallic materials with high technological characteristics, especially from a thermal point of view. 6. High energy density both at the inlet and outlet, with powers comparable to those of a gas turbine and more. 7. High flexibility. Ease of use is comparable to that of any internal combustion engine. 8. Greater safety and less maintenance due to the lack of destructive stress compared to internal combustion engines and gas turbines. 9. Reduced overall voluminousness. Any experimental prototype must be made not only to demonstrate the patented design but must also be able to be used for study purposes for its own completion with gas injection devices. For the cost of the prototyping itself, it is conceivable to build a machine with a total displacement of 2000 cubic cm and a maximum power output of 50 kilowatts. The number of revolutions can vary from a minimum of 1000 revolutions per minute to a maximum of 3000 revolutions per minute. Since fuel has to be used, the maximum temperature at the cylinder heads can be around 400 or 450 degrees centigrade. Depending on available funds, these parameters can of course be varied, as these are only general design guidelines. As far as the commercial aspects are concerned, it should be noted that the product is unique and that there are no comparable machines on the market. Having said this, it is obvious that the markets will be dominated by the first proposers of the product in the various energy sectors in which it is used, for example medium enthalpy geothermal and thermodynamic solar. That is all. Thank you for your attention.